So after having understood which is the end result of the problem, let's try to understand which was the process that has been used to investigate the case and to pinpoint where are the source of these unintended accelerations. I think that also looking at the process of the investigation is relevant. First of all, the Department of Justice of US decided to appoint a group of experts to investigate the case. As this case has been raised a lot of concern from the public opinion, a very well-renowned group of experts has been appointed to investigate the case. A group of people belonging to NASA. This is because NASA has a very good capability of investigating on accident to understand the complexity of a system that is made of millions of movable parts to find the source of the problem. Well, what is interesting to see is the type of reaction that Toyota had started interacting with the investigators. I don't know, it's like dealing with a recalcitrant kid. You know, when you are at home and you see that the chocolate is finished and your son is brown after having had all that chocolate, and you say, what you did? Nothing. Oh, this is more or less the reaction that Toyota had when being investigated. So they gave initially partial and misleading information to the investigators. The investigators were given with the source code of the main CPU that was powering the ECM. You remember that I showed you the picture of the ECM? We have a big guy and a little guy. So the big guy is a V850 CPU, and the application for controlling the throttle was running there. So the NASA investigators were given with the source code of that software. And then Toyota forgot to mention that also the little guy was a CPU running a software. And they didn't give the code to the investigator. Then the architecture of the ECM contains some memory module, RAM modules. The Toyota guys said that those modules were protected using EDAC. EDAC is a technique for adding additional bits, let me say, to each stored information. Those bits are there just to check whether the stored information is kept safe or not. Think about the parity bit. Have you ever heard about parity bit, I imagine? The parity bit is an additional bit that you put aside the stored information. The parity bit is computed in such a way that the stored information plus the bit is made of an even or odd number of bits, depending on what's your configuration. And if, when reading the stored information, you end up discovering that the number of ones there is not the expected, it means that something corrupted the stored information. And so you can tell, don't rely on that data because it is faulty. Well, let's say that EDAC stands for Error Detection and Correction Code, is a technique similar to the concept of the parity bit with something more. Besides being able to detect that the stored information is faulty, you can also correct it, okay? So let's imagine that you want to read you want to store in memory the position of the pedal, of the accelerator pedal. You can put an IDA code along with the stored information so that you always read the correct pedal position from memory. Well, the point is that even if Toyota designers say that the RAM was provided with FIDAC, it was not. And this is a problem. If there is a fault such that one bit of that memory is corrupted, as we do not have any IDA code, we are not able to tell that that data is corrupted. If it is the position of the throttle valve, you have troubles. Another issue is that within the code, you have critical variables. Those are variables that, if wrong, they could impact the correct behavior of the control loop. Think about a gain. Let's imagine that the command that you want to apply to the system has to be multiplied by a fixed constant gain. Okay? That is the multiplication factor of the command. And this is something that has been tuned by experimental test, such that at the end of the story, you have to put that constant to 1.5, whatever it is, okay? So the ECM makes the computation comes out, it is multiplied by 1.5, and then the result is applied to the system, okay? Then that is a critical variable. If that 1.5 becomes 15, you have 1 order of magnitude error in the command that you are applying. So that is a critical variable, okay? You cannot lose that variable. So the designer of Toyota said that those critical variables were duplicated. So instead of having just one constant, you have two that should store the same value. Before using that constant, you check whether the two replicas are consistent. If not, something is wrong, okay? You don't have to tell what happened that resulted in the modification of one of the two. What is important is that you are able to tell that something is wrong, and then stop everything, okay? We will see this later on. By the way, the designer of Toyota said, oh, we are duplicating each critical variable, but this is not the case. It is not true. And then they also said that during the computation of this software on top of the ECM, the amount of memory devoted to stack were used in the proper manner. Do you know what stack is? Is it clear to all of you? Okay. Let me say things in this way. Let's imagine that within RAM, there is a certain number of bytes devoted to store data. Okay? Let's imagine that you are doing a certain computation. The data that are involved in this computation, they are stored in RAM. Then there is another portion of the RAM that is a kind of container, general purpose container, that can be used whenever you need to use some memory for temporary placing there some content that cannot fit in the variables that you already allocated within RAM. Think about a function call. So you are in the main of your program and then you call function filter, okay? Maybe you provide to this function filter a number of arguments. Well, these arguments are placed in the stack, in this special portion of the memory. And then the function, when started, takes the inputs from that stack, makes the computation, and push back the result into the stack, so that your main can get the result of the filter function. Okay? So you have to imagine that this stack is a portion of RAM used as a container. This is a flexible container. It's a container that can be empty. And then this container can host data that you temporarily place there. And then the stack can be empty, it can become no longer empty, can start hosting some data. Then as long as the data are no longer needed, the stack becomes empty again. Okay? It is like you have your bathtub, you close the tube, you start pouring water within the tube, so you can see that the water starts to accumulate in the bathtub. Then when you are done with that water, you close the water and you open the plug, so the tube starts draining again. Okay, so that's the idea. Okay, what happens if you forget the water open and the tube is closed? When the water fills the entire tube, it starts going outside of the tube, okay? And if you continue to put water within our bathtub that is already full, the water goes downstairs, okay? And the people living in the flat below you starts argumenting, okay? So the Stack Overflow is the same story. You have a certain amount of memory that works as a stack that hosts data. And this stack can accommodate only for a fixed amount of data because you have a limited stack size. The stack size is not infinite. There are a few kilobytes devoted to that. So if your application by chance starts placing data within the stack without control, it may end up in overflowing the stack. So the application tries to put more data than what is the capability of the stack, and so the data are placed still in memory, but in positions that are not devoted to stack. So you are starting tainting the memory, okay? So the engineer of Toyota said that they analyzed the dynamic behavior of their code, and they end up saying, we are just using half of the memory that we have available as a stack. But this was not the case. The NASA investigator found that there was stack overflow, and this is very bad. Then, the investigations also pointed out that Toyota claimed that the electronic control system was able to mitigate the unintended acceleration because they put at work a certain amount of techniques to cope with all the possible misbehaviors. But remember that the EDAC was not there, and the critical variables were not duplicated. Okay, so the fail-safe was not so perfect as the Toyota people were saying. Another important element was found in the process, in the development process. We will go more in detail about this later on, but for the moment, let me say that when you write a piece of code for automotive, you may use C language as example. Well, you may have some memories from the past programming courses. You may remember that with C programs, you can do very nasty things. You can have dynamic memory allocation, you can have pointers pointing everywhere, doing everything. You can have an integer variable assigned to a floating point variable, or a floating point variable assigned to an integer variable, and the compiler just say oh, there is a warning, but doesn't stops the compilation, and so you end up with an executable code. Then, as all the student does, you don't take into the minimal consideration warnings, because if the compiler says there could be a problem, but generates an error, by definition there is no problem, but then generate the executable, by definition there is no problem because the executable is available. So you are typically ignoring any warning that the compiler may generate. So with C, if you don't pay enough attention, you can do very nasty things. This is because the Automotive Association decided to promote a subset of the C language that can be safely used in designing automotive application. This is conveyed in the MISRA guidelines. The MISRA guidelines is a book that tells you which is the subset of the C language that can be safely used when writing an automotive application. Give you an example. If you write in your application a switch, if you use the switch statement along with the cases that your application foresees, you must have the default case in such a way that if the variable that regulates the switch has a value that is not considered in the cases that you wrote, you still have a default action. So the purpose is try to constrain the designer so that the code does not exhibit any unforeseen hidden behavior. Okay, so Toyota were using an in-house coding rule that is not consistent with MISRA guidelines, and as we will see, this is a problem because the MISRA guideline was totally overlooked, wasn't mapped correctly on the Toyota guidelines, and a number of problems could have been avoided if following MISRA, while Toyota people didn't do. So let's have, for a moment, a look at which are the problems that we could have. Why the lack of EDAC and the lack of duplication of critical variables was a problem? The problem is that when you design a system that could end up in killing somebody, you have to have in mind always that your hardware will fail. You buy a chip from a certain vendor. You start using it in your application. Well, you have 100% confidence that that chip sooner or later will fail. Okay? So your electronic components will fail, full stop. This is something that you cannot avoid. Maybe it will fail in 100 years, maybe it will fail in one day, you don't know this, but it will fail. Then there are some statistics that shows you which is the expected failure rate for the components. So you can know in advance whether this will fail once every 1 billion hours or once every 10 hours. There are statistics that you can use, you can take into account when designing your hardware. But the starting point is that your component will fail. So all the design that you have to do must take into consideration the possibility of failure whenever the system you are designing is responsible for the life of somebody. Give you an example. If you take into consideration the memory bits in your system, you have a certain probability that the content of those memory bits changes unexpectedly, even if you are keeping the memory not operational. Think about your computer. The computer is powered up, you are doing something, you have a certain portion of memory that stores the code of your application that is not supposed to change, and then due to an unforeseen action, the content of 1 bit in that memory of code changes from 0 to 1. It could happen. This is because the semiconductor interacts with the natural radiation that is present everywhere in our Earth, and considering, for example, space mission in the space. And this interaction could produce a number of effects. One of these is called bit flip. So you have a neutron that hits your processor, and due to the interaction of the neutron with the atoms of the silicon, we have nuclear reactions that produce byproducts like alpha particles, and these alpha particles inject charges within the silicon. If you are so unlucky that the injected charge is released in a depletion region, there is an electric field there. We have charges free to move there, you have a parasitic current. If this parasitic current is happening in certain timing, in certain condition, whatever, we have a bit flip. So the stored 1 becomes a 0, or the stored 0 becomes 1. This seems science fiction, okay? So you may wonder, well, do we have to take care of that actually? Well, here is some numbers that are quite relevant. Well, if you consider natural radiation, if you consider a device working, let's say at sea level or at 4,000 meters, you can see that you have let me say, one of these bit flips every 10,000 to 100,000 hours per chip. So you take a memory chip, you solder on a board, you power up the board, you write a value on that chip, and then you wait, continuously reading the content of that chip. Well, once in 10,000 hours, if you are at the sea level, or 1 in 100,000 hours, if you are at 4,000 meters on top of a mountain, you will see 1 bit of that memory flipping. Okay? There is a friend of mine that is crazy as a horse that that designed a board full of memory chips. Then it was used to fly from Paris to Latin America and vice versa with a bag with that device operational. So this is a kind of risky business these days, okay? Because you may end up being confused for a terrorist. So you may have bad times if you do that when you are 10,000 meters on top of the Atlantic. But by the way, the result of the investigation that he reported said that during a 10 hours flight, he observed hundreds of memory corruption due to the radioactive environment that you can have at 10,000 meters when fly from Paris to Montevideo, for example. So this is something that happens. It really happens. 10,000 meters, the problem is much more significant than at sea level, but the problem at sea level cannot be neglected. Why? So let's imagine that we take into account this figure. So we know that once every 10,000 hours, 1 bit of memory is flipping. Then let's be optimistic. Let's say that just a small fraction of those memory bits is relevant, is visible in our application. What does it mean? If you have 1 megabyte of memory and your application is using only half of that, the half megabyte that is not used can be experiencing bit flip, but nobody cares. That memory is not used. Then, if we consider the half a megabyte that is actually used, we can have bit flips there. But let's imagine that we have a bit flip in a certain position in memory right before our application write a new value in that memory. Well, the bit flip is overwritten. Or, for example, let's imagine that we have a bit flip in a portion of memory that is used after the last usage of that specific memory location. The bit flip is there, but it will not have any effect. So, considering the total amount of possible faults that could happen in your memory, only a small portion is really important, because only if the bit flip arrives in the memory that stores a value right before that value is read, the faulty value can spread within the system. Okay? So only a small portion of faults are relevant for our considerations. So let's say just 2%. So this means that we can have dangerous faults 0.2 times per million hours. So something very, very small. Then let's assume that that chip that is experiencing that failure rate is driven 1 hour per day. So you take your car from Corso Dante, you come to work here at Politecnico, half an hour one way, and then you go back in the evening, another half an hour the other way, okay? So, if we consider a particular family of cars, like Camry vehicles, built in 1 year, that is about 430,000 vehicles, well, this possible number of errors when using the car 1 hour per day gives that one of the vehicles of this 430,000 fleet will be subject to one dangerous fault every 12 days per chip. So let's imagine that you have 430,000 vehicles. Okay, each is using one chip. So you have 430,000 chips. Okay, each chip is used 1 hour per day. Each chip can be subject to a dangerous fault every 0.2 times per million hours. So you have the chance of that faulty chip kills somebody every 12 days, okay? And in the car, you don't have just one chip. You have hundreds of thousands of that, okay? So you risk to kill somebody every hour, probably. And you are just considering one type of vehicle, 1 year of production, okay? So, we are not kidding here. So these faults will happen. These faults will kill somebody. So we have to design taking into proper attention those behaviors, because otherwise somebody will ask you to pay for your failing design. This is relevant because those chips could store your software. Then if the software is changed without nobody noticing this, you could have a failure in your application. So you ask for braking and the car doesn't brake. You don't ask for full 100% acceleration and the car does 100% acceleration, okay? These are the problems we have to cope with. So the investigation found that the techniques that Toyota deployed in the ECTM for coping with those type of faults was defective and inadequate. What does it mean? We start from the point that faults will happen, okay? It's kind of Murphy's laws. Whatever that can go wrong will go wrong, okay? This is the Murphy's law. And it's the same story. Failure will happen. So the designer decided to add inside the system techniques for coping with these failures. So once you recognize that you will have a problem, you have to put at work techniques to mitigate the effect of that problem. So you cannot avoid to have a memory corruption, but you can recognize that that will be a problem, and you can be ready to detect when that memory corruption happened. And you can put at work proper corrective actions, okay? These are the fail-safe techniques. Give you an example. Let's imagine that you are driving, okay? The way in which you drive on a dry road is very different from the way you drive when the road is icy, okay? So you recognize the problem, the road is icy, you put at work some preventive techniques. You reduce the speed and you try to use as less as possible the brakes, okay? Here is the same story. You recognize that there will be a problem in your hardware, then you embed in your system techniques to confine the possible misbehavior due to that fault. We will understand that later on during the class. For the moment, let me just say that all the techniques that you put at work in your system for avoiding that a fault kill somebody is called file-safe technique. It will fail, but even if failing, it will be safe. Nobody will be killed, okay? So the file-safe technique that TCS was using was defective and inadequate. So the technique was not able to confine the chain of events originated by a fault, resulting in a severe misbehavior. The redundancy, so the amount of additional features placed in the system for file-safe purposes was inadequate, and there were single point of failure. Let me try to explain this concept. Let's imagine that you want to pick up the position of the accelerator pedal, okay? You can have a switch there that is a kind of potentiometer that is able to understand which is the position of the accelerator pedal. That potentiometer goes through an ADC converter to the microcontroller so that we can convert the analog angular position of the accelerator into a digital value. Okay? So the designer of Toyota decided to have two switches. This is a kind of redundancy. In my nominal application, I just need to have one potentiometer. But as that potentiometer can be faulty, I add another one. So one of the two will work. Okay? So the ETCS is able to read 2 times the accelerator position. One of the two will be good. So if one potentiometer is broken, the other one will work. Okay? The problem is that both the potentiometer were read using the same ADC converter. So we have two switches. That's okay. If this breaks, this is working, or vice versa. But then the conversion between the analog values into digital values was done using a single component. What happens if that single component breaks? We have two accelerator readouts that are faulty because they are produced by a broken converter. That is the single point of failure. No matter if you have duplication, the duplication converges versus a single component that could introduce a fault in your system. Okay? So this is an example of existence of single point of failure and inadequate redundancy. Even if we have two switches, we still have a problem because we have only one ADC. We need to use two switches and two ADCs. In this way, we are sure that we are acquiring the position of the pedal through two independent channels, and so one of the two will be correct. Okay? Is this clear? Then, another interesting aspect can be found if we analyze the source code of the ETCS software. Well, as I said, our reference is the MISRA C guideline. I again underline this fact. MISRA C guideline is a book telling you which is the subset of C language that is safe when developing automotive applications. What does it mean? You cannot use recursion. You cannot use dynamic memory allocation. You cannot use implicit data type conversion. You have to put comments. You have to initialize each global variable, and so on and so forth. So this book contains a number of rules. As we will see later on, part of these rules are, let me say, suggested. Some of these rules are compulsory. Okay? Well, Toyota claimed that half of the MISRA C rules was covered by the internal coding styles. But in reality, out of 127 rules of MISRA C, only 11 were covered by the Toyota rules. So less than 10%. Then in some cases, Toyota did not follow its own rules. So they decided to use their own rules because they considered that better than the MISRA guidelines. But at the end, they even didn't follow their own rules. Then out of 35 MISRA rules, 14 of them were violated for about 7,000 violations. Then if we look to the newest edition of MISRA C, so the edition 2004, the number of violations summed up to 80,000. just give me to show you some of these violations. So in the code, we had 2,272 global variables declared with different types. What does it mean? Let's imagine that you develop your application in multiple files, 2 files. In one file, you declare a function as, you declare a variable as extern int something, and extern int temperature. Then, in another file, you define float temperature. The name is the same. So, as in one file is declared as extern, and the other one is declared as not extern, this means that you will end up with one single object, temperature, that is visible by both files. But in one case, you are treating this as float. In the other one, you are treating that as int. Guess what? When in some part of your code you store the temperature 25.5, on the other code, if you are lucky, you will have just 25. Okay? So there is a mismatch between data type. Other failure is unsafe typecast. What does it mean? You may remember that in C code, you can take, for example, a float variable. You can use it as a value to be assigned to an integer variable. So float temperature, int conversion equal temperature. You can do that. C language doesn't forbid this operation. If you compile your code, you will have a warning, implicit cast conversion. But we don't care about warnings, because at the end we still have the executable, so who cares? Well, no, this is a problem. You have unsafe cast, typecast, because you can change the stored information. Okay. Other problem, you have a 32-bit integer and you assign the value to a char variable. You can do that, no problem. But you are compressing 2 out of 32 values into 2 out of 6, to the power of 8 values. You will have some problems there. Other problem, you have variables that are defined but not initialized. This is something that we always do. So we define a variable, we don't give an initial value, and then we read the content of that variable as first operation. You did this error for sure in the first program that you wrote. I'm sure of that, 100% sure. So if you use an not initialized variable, you can't assume an initial value there. It depends on where the variable is stored. If it is stored in a register within the CPU, it depends on what happened to that register before you started using the register for that variable. If you store this in main memory, you don't know. It could be 0, but it could be whatever. Another problem, again, typical programming problem. We had 2 arrays of 16 bytes that were initialized to 17 bytes. So, typical programming example, char array 16. So you have an array of 16 records. What happens if you do array 16 equal to 0? You are writing to 1 byte past the end of the array. You can do that in C code, no problem. The problem is that that code will write the 17th byte, you don't know where in memory. It could be in the first byte of the next variable you defined after the array. It could be in the interrupt vector table of your processor. You don't know. Okay. The guidelines, the MISRA C guidelines, are intended for helping you in avoiding this kind of problems. The guideline says you cannot do implicit typecast. Okay. So if you take a variable that is char and you assign it to an integer variable, that is an implicit typecast, unless you specify the cast. So you put in brackets the data type to make the conversion. That is an explicit typecast. Well, in some cases, the typecast, even if implicit, are safe. If you take an 8-bit variables and you store the value in a 16-bit variables, who cares? There is plenty of room there, no problem. The problem is the opposite. If you take a 32-bit variables and you store it in an 8-bit variables, there is a problem because the two sizes mismatch. So these are things that could happen. If you have coding rules that forbid you to do that kind of operation, you will not have troubles when running your code. So the guidelines are there for making you able to write better code. It doesn't mean that it's more efficient. Okay? It doesn't mean it is smaller. It means that you will be more likely to be able to test your code. It will be a code with less implicit behavior that you hadn't considered when writing your code. So the quality of the code will be better. So if you are working in a company writing firmware for automotive, you must use MISRA. If you are working in a company writing code for aerospace, if it is avionic, you must follow another rule that is 178 A, B, or C, depends. But again, there you have guidelines. If you are working in the space business, you will use MISRA plus other specific rules crafted for the space business. Okay. Another problem that the investigator found was that the code used a lot of global variables. Well, this is a big issue because if you have global variable, any portion of your code can access those variables. And so if you have side effects, you can have some function to tint some of those global variables, and you are not able to understand that. Think about this scenario. You have the array char vector 16. The next statement in your code, it will be int alpha. Okay? So you have an array, and then after that you have a variable. When you compile this code, in the RAM memory of your processor, you will have 16 bytes for the vector, and right after that you will have 4 bytes for alpha. Okay? Let's imagine that we have one function that is writing 1 byte past the vector, and another function that is reading alpha. So you have that the function 1 will write in the first byte of alpha, and the other function will read alpha without knowing that somebody else changed the content. This is because you are using global variables. This is because you are not putting too much attention on the code that you are writing. This will create a huge problem. If this happens, normally the compiler doesn't tell you nothing, the problem doesn't show up only in the particular case when you write the 17th byte and then you read alpha, and you will spend hours debugging this code, I can tell you. Then, in the code, 82% of the data object were declared with unlimited scope and with open accessibility to anybody. So this is very risky. If something goes wrong, it will taint the code, and you will have no way of detecting the problem. You will just see the unintended acceleration. The analysis shown that this 82% of object corresponds to 10,000 global variables. Most of them could be static, local static. Some of them could be file static. This means that these 10,000 global variables can have limited visibility. This means that you can cleverly select which kind of global variable that could be. So you can constrain the software in being not able to access to most of these global variables, because basically it is not needed. So you can save a lot of problems. Another problem is that those variables that were really global, well, they were used without mutual exclusion. Those of you that did real-time operating system, industrial network, real-time operating system should have clear in mind the concept of mutual exclusion. Those of you that did the operating system for embedded system with me, I hope they have a good idea of mutual exclusion problem. Just let me recap the problem. When you have a global variable, that is a shared object. This means that you can have different user of that global resource, shared resource. Well, in order to avoid race condition, you must access that shared resource using mutual exclusion. This means that only one task at a time can have the right of using that shared resource. The other shall wait. This can be done using semaphore or can be done using disabled interrupts. This is because if you have a semaphore, you can have a task that preempts the running task that tries to get the resource that is blocked by a semaphore, and so the task is blocked. So it is not allowed to continue. If you have interrupt disabled, you don't have preemption. So the task that owns the shared variable continues to use it until it is done. Well, this was not happening in the ETCS software. This means that you can have preemption, you can have one task putting a value in the shared object, then you can have again preemption, another task put another value in the shared object, and then you don't know which is the real value in that object. Okay? This is a race condition. Another really nice thing that has been found in the ETCS software is the way in which watchdog timer were used. Let me explain this. We said that we have the main processor doing the activity and the coprocessor checking what the main processor was doing. Okay, you remember that? So one way of doing this checking is through watchdogs. It is very simple. The main processor says to the coprocessor, I am starting this function. This function will run for 10 milliseconds. In response to this message, the coprocessor starts a timer programmed to expire within 10 milliseconds. If the coprocessor sees the timer expiring, it means that in 10 milliseconds, the main processor did not complete the activity. Conversely, if the main processor completes the activity, it says to the coprocessor, I finished, and so the coprocessor stops the timer. Okay? This technique is called watchdog. So you start an activity, you set a timer. If the timer expires before you stop the activity and you reset the timer, something went wrong. Okay? Is this clear? So, in order to make the proper use of this technique, your software must set the timer, do the intended operation, reset the timer. Okay? In this way, the watchdog is able to tell whether the main processor completed the activity in the proper time. Okay? So if we analyze the software of the ETCS, we find that the designer of Toyota were very smart. So they said, oh, I don't want to change my software. It is a burden to start the watchdog and then do my activity and then stop the watchdog. Let's do a different thing. Let's have an hardware timer on the main processor that is programmed so that every 10 milliseconds resets the watchdog. So the software can do whatever it wants. The software doesn't have to take care of handling the watchdog. There is the hardware timer. Guess what? The hardware timer works independently from the software. So even if the software is broken and it is not able to complete the activity in 10 milliseconds, the hardware timer does. So the watchdog is convinced that the processor is working correctly because there is an hardware timer that resets the watchdog, even if the main software is blocked. Clearly, this way of implementing these techniques violate the concept of the watchdog. Okay? So this is another example of inadequate fail-safe operations. The way in which the watchdog was implemented deceives the purpose of the watchdog itself. So the fail-safe technique was not able to detect the occurrence of real problems. Another thing that is interesting is to analyze the algorithm that ETCS software implements. So far we analyzed the hardware, we analyzed the fail-safe techniques. Now let's look at the algorithm. So the way in which ETCS is actually implemented, which is the algorithm that is used there. Well, no matter what your professor of advanced programming says, in automotive, recursion is forbidden. So if you are writing automotive software, you cannot write recursive algorithms. Any international coding rules forbids the use of recursion. So even if you spend a lot of effort for passing advanced programming, now you can forget about recursion, okay? I see many of you that are happy, good. So, why recursion is forbidden? This is because if you do a recursive algorithm, it is because you don't know in advance how many iterations you have to do in your algorithm. You don't know in advance how much iteration you have to do. So if you don't know in advance how many iterations you have to do, you don't know in advance how many resources you will use. Think about stack usage. We said that a stack is a portion of memory for depositing temporary value. Let's imagine that each time you do one step in your recursion, you deposit a new value there. So the stack grows continuously at every iteration of the recursion. If you don't know how many iterations you have to do, you don't know how big your stack could be. Simply speaking, you are not able to tell in advance. This is a problem, because you are not able to tell whether the amount of stack that you reserved for your system is correct. The stack size is something that you define during the configuration of your system. So you cannot change that when the system is running. So if by chance your recursive algorithms takes as input variables, data, that requires more recursion than what you think was needed, you have a problem, because you will have stack overflow. And this is what was happening on the ETCS software. Recursion was used, so it was using more stack space than what it was decided to use, and the stack overflow resulted in overwriting some critical memory area, in particular those memory area that was storing portion of the operating system of the ETCS. So it is pretty much the same that happens when you have your Windows application that starts becoming crazy. There is no protection in your system and you have the blue screen of that. More or less this is the case. So your application do an endless recursion, you have a stack overflow, the data that are overflowing the stack are corrupting the portion of memory where you have the operating system, you have the blue screen of that. The problem is that here you are not running a desktop or a laptop computer, you're driving a car. And the blue screen of that corresponds to the throttle valve full open. So you have unintended acceleration. And this is what happened. So the chain of event is most likely this one. We have a recursion. The recursion produces the stack overflow. The stack overflow overwrite a critical portion of the real-time operating system. This was a no-ZEC real-time operating system. This is not relevant. What is relevant is that the overflown data tainted the operating system. This overwriting of the operating system resulted in the sudden termination of a task of the application, task X. Task X was responsible for computing the angular position of the throttle valve, plus running the file-safe functionalities of the ETCS. Due to the stack overflow, the task is broken. It cannot run any longer. As this task was particularly important, there was a watchdog associated with that task. But the watchdog was handled using an hardware timer. So the watchdog was not aware of the death of the task. The result was that the chain of event led to the throttle valve opened 100%. So we have the unintended acceleration, okay? So the result of this is a combination of different elements. We have a mistake due to the process. The designer didn't follow coding guidelines. The result was that the application was faulty. We had stack overflow due to recursion. Then there was a wrong implementation of the file save technique. Instead of using the watchdog properly, triggering, stopping it through the application, we are using an hardware timer. And at the end, there is a problem with the testing of our system, because the amount of testing that was done at Toyota to analyze all the possible working conditions of this system was simple, not able to identify this chain of events. Okay? So there is a problem of development process, there is a problem of techniques implemented in the system, there is a problem of validation. So nobody was able to predict this chain of events. Okay? So here we have plenty of room for improving. We have to have a better development process that is based on strict rules that have to be implemented and checked. We have to divide our development process in steps. Each step is regulated by a very well-defined set of operations that must be done. And then we have a gate. We cannot move in the next design step unless we are sure that what we have done in this step is consistent with what we have to do. Okay? So, you may say, oh, the problem is that we haven't tested enough our device. So we have to do more road testing. So we have our system, we build our fleet of vehicles, we have 1,000 vehicles that we are using for testing campaigns before bringing this vehicle to the market. Okay? Well, the sad story is that automotive systems are so complex that road testing is not enough. You will not have the chance of considering all the possible corner cases. You are not convinced of this? Look here. Toyota said in 5 years we had 35 million miles of testing for our vehicles. We tested our vehicle for 11 million hours. Okay, so this seems very huge numbers. So 35 million miles. I don't know how many times we can circle the Earth with this amount of miles. So we did 11 million hours of test. So again, impressive. But then try to take this number and divide this by the number of vehicles that has been produced in 5 years. It means that they tested the vehicle from 1 to 2 hours per vehicle. Okay. So 2 hour driving your vehicle. Do you think you are able to consider all the possible conditions? It is not possible. You have 50 electronic control units interacting with mechanical parts, working together. So you have, I think, a space of possible conditions that is not imaginable. And you think that you are able to cover all these possible conditions in 2 hours. It is impossible. The sad story is that the test is done by the end user. So if there is a problem, like unintended acceleration, it is not the designer that discovers it with this process. It is not the tester, the test driver that discovers it. It is the user. So the 89 users that were killed. Okay? So this long story, I think, gave us an understanding of the problems. If we do not comply with a good best practice in designing, that means doing the operations in a well-defined order, having check gates to verify that each step has been done properly before moving to the next step. If we don't comply to guidelines that are de facto standards recognized by a certain industry as the best way of doing things, if we don't do enough validation of our system before reaching to the road test, we will end up with critical problems, okay? So what I'm trying to give you in the next lectures is a set of, we say, techniques to address in a structured way the design and validation phases that are needed for developing successfully automotive applications. Please bear in mind that this is not a magic wand that gives you the power of building perfect automotive software. If at the end the control that you are designing is crap, nothing will happen. It can be shaped in the best way, okay, just to be rude. You can comply with each international regulations. You can do whatever testing techniques you want, but at the end, if your algorithm is wrong, you have something perfect that is, anyway, behaving wrongly. So, being a good designer means be able to write a good control algorithm, a good piece of software. But if this software, this algorithm, is not crafted according to a certain best practice, you can have the risk of side effects that can be very dangerous, okay? So, what I'm saying, this is to say that this course doesn't give you the magic wand to solve all the problems. You have to be a designer to do good designs, and then you have to be a disciplined designer so that your good design is deployed in a good manner, okay? Then, let me spend a few minutes more to look into another definition. So now we are done with the safety critical systems. I hope you are now convinced that this is a big issue, okay? Now let's look into another type of critical systems, the mission critical systems. Mission critical systems are systems where wrong behaviors can cause the loss of huge amount of money. Okay, so with mission critical, we look to the economic value that we are losing due to failures. The same concept applies. Things will go wrong. Are we ready? So if things goes wrong, what we do to be safe? In this case, the parameter that drives us is not the loss of human lives. It is the loss of money. Just to give you an example, think about the Ariane 5 maiden launch. Ariane 5 is today the biggest European vehicle to ship satellites to space. Okay, so you can use, if you are willing to put in orbit a telecom satellite designed in Europe, you will use Ariane, most likely. If you want to bring to space a scientific mission, most likely you will use a Proton vehicle from Russia. This is because it is cheaper. If you are in the US, you will most likely use the Atlas launcher. So in Europe, we have Ariane. Ariane 5 is the last generation of a series of vectors. There was Ariane 1, Ariane 2, Ariane 3, Ariane 4, and then in 1996, Airbus decided to, well, was able to test Ariane 5. Today, Airbus is designing Ariane 6. Okay. So, These kind of launchers are very expensive, like 30 million euros each missile, okay? So one missile that is one-time only device is 30 million, more or less. So you use this only one time. And better if that time is the right one. Otherwise, you can lose a lot of money. Maybe you don't have an idea, but could you have, let's do this. Think about a telecom satellite. So the satellite that is able to serve the communication for the whole Europe, okay? Do you have a rough idea of the cost? Is it in the range of hundreds of millions, billions, whatever? More or less, one telecom satellite is about 1.5 billions, more or less. Have you an idea of which is the expected lifetime for such a satellite? 10 years. 10 years, correct. So you have to develop a design that costs 1.5 billions and that stays in space for 10 years. Do you have an idea of how much time it takes to break even? So how long it takes to repay the 1.5 billions through the revenues that that satellite generates? It's 2 years. So you have a system that you ship to space that will work for 10 years. It costs 1.5 billions. You pay that in 2 years, and then you have 8 years of revenues. So do the math. 1.5 by 8. It's a big number. So if Ariane fails in shipping to space that device, you lose 12 billion euros. Okay? So it is worth paying 30 millions for that launcher, provided that the launcher is safe and is able to ship to space the satellite safely. This is an example of mission-critical system. So if the system fails, you don't lose just 30 millions. You lose 12 billions, okay? So what happens during the maiden launch of Ariane 5? No payload there, so no telecom satellite there, just the empty container plus the launcher. Well, what happened is that after 30 seconds of the liftoff, there was a problem in the controller of the altitude of the launcher, and the command that the onboard computer was sending to the thruster generated a lot of structural tension, much more than what was tolerated by the structure. So the protection system embedded in the launcher recognized the risk for a failure, for a mechanical failure due to the fatigue of the material, and so triggered the explosion of the launcher. So let's say half a minute after liftoff, the launcher exploded. Well, that was a very bad maiden launch, because it was not possible to ship the empty container to space, okay? So the failure was due to, guess what, a software failure. So it is interesting to analyze the root causes of this. Let me say, the electronics on board of the launcher, to the very essential, is schematized here. So this electronic is implementing a closed control loop. There is a desired trajectory. There is an inertial platform to detect which is the current status of the launcher. Then there is an onboard computer that takes this inertial platform output data matches this with the desired position and decides how to operate the engines to follow the desired cruise, okay? As the designer recognized that things can go wrong, they decided to duplicate everything. So we have two inertial systems that works in parallel, two onboard computer that works in parallel, and then when they come to an agreement, they drive the engine, okay? So this is an example of redundancy. The mission can be completed using one pair of inertial platform plus onboard computer. But as we could have failure in one of the two, we add a redundant pair. So we add another inertial platform, another onboard computer. These are not needed for running the control algorithm. This pair is enough, but for preventing misbehavior due to one of the two components failing, we add a backup, okay? This is the example of redundancy. What we have here is not strictly necessary for the function we have to implement. We are placing those elements there for preventing misbehavior due to failures, okay? Is this clear? Then, what happened here? Well, the software failure happened when the inertial platform tried to convert a 64-bit floating point number into a 16-bit integer. This caused an overflow. We have a 64-bit values, very huge value. We try to squeeze this in 16 bits. It's not possible. You lose precision. This resulted in an overflow. Well, the overflow is an arithmetic overflow is a bad situation because it could trigger an exception. That is, the processor is working normally. When the overflow happens, a special piece of code is executed to handle this overflow. This is typically a user-provided code. It is the user that knows what to do when an overflow occurs. Well, the problem is that nobody was there to provide the proper code to handle that exception. The result was that the inertial platform stopped operating, providing erroneous data to the onboard computer. Well, as the two inertial platforms were identical, both was experiencing the same software fault. Both stopped working. Both started producing wrong value to the onboard computer. And so, even if it was redundant, there was a single point of failure. The two failed at the same time. The two stopped providing the correct position at the same time. The onboard computer was receiving a faulty data, but both the inertial platform were providing the same faulty data. So the onboard computer thought that the data was correct. So the onboard computer computed the correction to be applied to the thruster based on faulty data, and there was no way of understanding that the data was faulty. The result was the explosion. So why we have this situation? Again, here we have a process problem. The inertial platform on board Ariane 5 was reused from the previous generation, Ariane 4. The problem is that Ariane 4 is a much smaller vehicle than Ariane 5. So the phenomena that could happen inside Ariane 4 have a lesser magnitude than what could happen in Ariane 5. So the code on top of the inertial platform that was okay for Ariane 4 was not okay for Ariane 5. So the result was that the code currently working on Ariane 4 had a big problem in dealing with the data produced by the Ariane 5. The result was the stack overflow, the arithmetic operation overflow. But what is even most surprising is that the failing function was not needed in Ariane 5. So that function was useful in Ariane 4, not in Ariane 5. But the manager decided not to remove that function from the code. So this function, from the Ariane 5 point of view, was a useless function. Why do they decide to keep it there? Well, you have to imagine that one of the costs, as we will learn later on in this class, associated with software development is software testing. I think that considering the overall development process of a piece of software, half of the cost is writing the code, half of the cost is testing it. So if you are dealing with a big project as the software for a rocket, the cost of software development and testing is some millions. If you can save some of this, you will be happy. So the manager decided not to remove F, otherwise the test shall be repeated. Every time you change your code, you have to test for non-regression. So you have to be sure that whatever it was working before removing the function is still working after the function has been removed. And this will have implied a lot of cost. So they said, okay, the function is not needed. We keep it there because it will not hurt. It is doing nothing. We will not use the result of that function. So keep it there so we don't have to retest everything. Okay, this is the idea. The problem is that even if the function wasn't used, it was active, it was operational. The result was not used, but the function was operational. And then we had the bad luck that the function, using much bigger data than what it was intended for, resulted in an overflow, not handled properly, and thus there was the failure of the mission. So the message here is that you have to take into great care the code that you're writing. Reusing is a good thing, but if you reuse, you need to have always live code. Dead code is dangerous, because if it is dead, you are not supposed to use it, but if you keep it in your system, it could be activated by unforeseeable situation, and that code could become alive, and thus corrupting your system. So you must avoid to have that code. So the software failures that we have seen leading to problems in safety critical system and in mission critical system is due to the complexity, is due to the intrinsic complexity of software. We must have a disciplined approach to software design and development and testing. Otherwise, we will not be able to master this complexity. And testing, just brute force testing, is not the problem. So if it's not the solution to the problem, let's say that you neglect the process, you neglect the guidelines, you do software in the first way that comes to your mind, and then you say, okay, I don't care, I write spaghetti code and then I test it. I test my code exhaustively. So I can be sure that even if my code is not perfect, I know whether it is failing or not. It is not possible. The software is so complex that the amount of testing that you have to do for completing an exhaustive testing is not affordable. You need so much time that probably when you are done with the exhaustive testing, your software is already obsolete, so you will not use it. So, in order to avoid software failures, you need to have a disciplined approach. So you must use the proper process. You must follow the proper techniques. In the rest of the class, we will start looking at the ISO26262 as guidelines for being disciplined in our design. So I am done with this lecture. Do you have any question? Okay. Remember that next Wednesday we have no class. We meet again on Friday. Okay?